Hello everyone, this is Professor DePaulo welcoming you to Psych 220 Behavioral Statistics Online. And today's lesson, I will be just giving sort of an introduction to statistics, what they are, what they're used for, some of the problems that accompany statistics. And this will sort of serve as the foundation for the material moving forward. So in chapter 1, I'm going to be talking about the statistical terms that you need to know. The measurement issue, so I'm really into measurement, and so I'll talk about measurement constantly. It's at the heart of psychology as measurement because it's so difficult to measure things in psychology, I would say. The research terms, that if you're going to do a correlational or descriptive study versus an experimental project, knowing the places of statistics and science in general, and understanding some basic summation notation, which you've probably seen before. So statistics requires math skills, and that's why I'm having you do Appendix A. I'm not having you do it, I'm having you read it and go through it just to make sure you know the basic statistics that you need to get through in the course. This is not a calculus course, obviously. This is a very minimal amount of algebra used. I would say the vast majority of the course is just basic computation. So if you know your PEMDAS, please excuse my dear Aunt Sally, order of operations, right? If you know how to use exponents, if you know how to work addition, subtraction, multiplication, division, which is PEMDAS, from left to right, you should be fine. There's very little about solving for variables. There might be some really simplistic equations with one variable to solve for, but it's basic stuff. Yeah, if you go into statistics, especially multivariate statistics at an advanced level, you're going to have a much more difficult time because we're talking about now matrices versus just linear equations. Here we're dealing with one equation. If you're doing multivariate, you're dealing with multiple equations, and that equals a matrix. So we're not going to talk at all about that stuff, but it does get harder. It does require more math as you get to more advanced levels. For many of you, you're not going to see more advanced levels. For a few of you that go to graduate school and take much more in-depth statistics, you're going to see more advanced stuff. And depending on if you go into research or you're just interested in statistics in general, you'll see multivariate probably in graduate school. Now, most of you are psych majors and you probably don't want to be in this course. However, this course is important. One, because you're taking it at BMCC and you're taking it with me, and I've taught this course for almost two decades. No, not quite 2 decades, probably 14, 15 years. And this is my favorite course to teach, amazingly, right? Some of you are like, that's kind of impossible to believe. But it is my favorite course to teach, and I've taught it many years at Rutgers, and now I've taught it at CUNY at BMCC. It is really important because you're going to be having this again and again and again. If you go to the four-year college, hopefully they take this course as transfer credit. You don't have to take it again at the four-year college. But if you don't take it at the four-year college, you're definitely going to see it in graduate school. So if you want to do your master's degree in counseling, you're going to see statistics. It's just something that you can't get rid of. It's basically everywhere. Data analysis is anywhere you work, even at Starbucks, even in a grocery store. You're going to see data analysis. So it's something that you want to, if you don't enjoy it, you want to be comfortable with it. It's going to help you. You should have some basic skills, though, in computation and really elementary algebra to do the course. It's nothing really that you haven't seen before, but you should feel comfortable. So review Appendix A, be comfortable with it, and then you'll be ready to start the course. If you have questions, you can always see me or come to the office hours and we can talk about it. So statistics means statistical procedures. And there's a couple of different branches of stats that I'm going to go into, but we use stats to organize or summarize information and draw conclusions. Because without stats to draw conclusions, you have basically philosophy. And philosophy is a great, subject. I mean, I love philosophy. I mean, I really recommend everybody to take at least one philosophy course because it gets you to think critically about life, about the world, about things we take for granted. It'll help you become, a better researcher, a better scientist, a better practitioner, a better, basically any job that you engage in. I really feel that strongly about philosophy. The problem with philosophy is it rests on argument. And people develop all kinds of complex arguments about things we can't measure, like the existence of God. And they'll come up with, a series of arguments in favor of God, and there's a series of arguments against God. And as a psychologist, as a researcher, as a stat person, I'm not going to test that idea because I can't measure it. Right? I'm not going to go by just a logical, rational, strong argument written in words. When I decide whether something exists or doesn't exist, I'm looking at data. What does the data tell me? Well, what is the probability of what I believe to be the case to actually be the case? Basically, what's the probability of my hypothesis being supported? I don't like to use the word prove or disprove because you will never be 100% certain in statistics. Statistics is based on probability, and at the two extremes you have a probability of 0, which means the event is impossible, and you have a probability of 1, which means the event is certain. But in the real world, you never have 0 or 1, you have something in between. And so though statistics is very strong for supporting an argument, showing research, supporting hypotheses, I will not say prove or disprove, because there's always a chance we make a mistake with statistics. It's never 100% anything. So just keep that in mind. People like to write, it is now proven, we support our hypothesis, it is proven. No, it's not. It's never proven. It's supported. But it can never be proven nor disproven because we can never have a probability of 1 in real life or 0 in most things we're looking to actually study, right? So that's a little based on what statistics tells us. Our goal of statistics basically is to summarize information and interpret it, usually generalizing the results from a small group to a larger group, or what I'll be talking about from the sample to the population. Your population is everybody you're interested in studying. So if we were interested in studying BMCC students, it would be all 25,000 or 20-something thousand BMCC students enrolled. Now that's a hell of a lot of students to study, 25,000. So we generally don't study 25,000 because I don't have the time, nor do I have the money, nor do I have the motivation to study 25,000 people, because I would have to basically run my study on all 25,000 of those students. That's not realistic in most cases unless your population is extremely specialized and it's very limited. But in most studies, in the vast majority, close to 100% of studies, our population is almost infinitely large. If you want to say college students at BMCC, that's a pretty small population of 20-something thousand. That seems really big to us, but if I said college students in the US, now we're talking about millions. And there's no way you're doing research with millions of people. So instead, we settle for studying the sample. The sample is a subset of the population, and we want to draw conclusions about the population by using the sample. So I may study 100 people, and then want to generalize conclusions to the population of millions or thousands. Is it perfect? No. There's always a chance that your sample is not really going to represent or be representative of the population. However, a lot of times your sample is a pretty good indication of the population, and we go with that. So our goal as researchers is to take a small subset of the population, the sample, and use it to study and derive conclusions or draw conclusions about everybody we're interested in studying, which is the population. So here's basically a slide summarizing what I just said. The population is everyone we're interested in. The sample is a subset of the population, a small portion of the population. So I select the sample, and there's a variety of ways to get the sample. There's better ways to get the sample, and there's worse ways to get a sample. We'll talk about that. And based on our sample, the results in our sample, so whatever research we're doing, whatever study we're conducting, the results in my sample, which could be 100, could be 500, could be 1,000, could be as small as 30. I had a study where I had 30 people. We were studying meditation. I could only get 30 people because I couldn't get enough students to stay in the study. They just kept getting busy and not coming back. And the study was run for about 10 weeks, and trying to get BMCC students to show up 10 weeks in a row to participate in your study is very difficult. So at the end, I had like 30 people, and I started with like over 100. So the sample could be a variety of sizes, but 100, 200 in psychology, that's a pretty reasonable sample. If you're doing online research with the general population, your sample might be thousands. If you're an economist and you're studying all kinds of stuff you can collect online, your sample may be 10,000. So, what's a better sample? The larger sample is generally better, but it's not always feasible to get a really large sample. It's very costly and very time consuming. So in psychology, 100, 200, I would be very satisfied with that, but I could be satisfied with less. And based on our sample, we generalize those results from our sample to the population at large. That's the goal. So when we're conducting research, we're measuring things. We're measuring variables. These are characteristics of individuals or situations that have different values. So a variable could be gender, and the values could be male, female, non-binary, as are 3 possible values for gender. Or the variable could be ethnicity, and you could have Italian Americans, Asian Americans, African Americans, Hispanic Americans. You can have a variety of different ethnic groups. You could also have variables that are not categories. So what I gave you are categorical variables. You could have what are called continuous variables, or what I'll discuss later, interval scaled variables or ratio scaled variables, or you have many, many values. For example, GPA, that could be a variable, and there's many possible values if you measure GPA out to hundredths of the decimal point. So your GPA could be 3.7857, and someone else's GPA could be 3.7870. You see how many different values you can have for something like GPA. So different types of variables can have either a finite set of values or basically a near infinite set of values. Data are measurements. So we're usually measuring the variable, and the data is just basically information. It's what that value is. So if I'm looking at your GPA, the data is your GPA, right? Of all the participants, they all have a GPA. That's my data for GPA. My data for gender is your gender. I have the whole group of people in my sample. So measurements or observations of a variable are called data. If you don't have data, then you can't do statistics. So data is kind of a prerequisite for doing statistical analysis. Data set is basically all your variables. So if data is for one variable, your data set is all the variables you're measuring in your study and all the values they take on. And so I can collect in a study, I can have 50 variables, 100 variables easily. And if I collect information, if I collect data for all those 100 variables, I'm going to have a data set. And then I have to organize it, then I have to analyze it, I have to enter it into some kind of package and analyze it. And we're going to be talking about Excel in this class, mainly because SPSS is what I generally teach, but we don't have access to the lab. So to have you access SPSS remotely would be problematic because students have all kinds of issues getting onto the portal. I mean, the portal exists. You can try to get onto the portal, and I'll talk about that later in the course. The problem is I can't expect everyone to get to the portal because students always have problems accessing the remote SPSS server, and the server might actually shut down if too many people are using it at once. So we're going to use Excel. Excel is free. If you're a BMCC student, you have access to Office 365 for free. Take advantage of that. You could do a bunch of things in Excel. Is it the best package for data analysis? No, but it's something that is useful, and I've used it in my career in corporate, when I worked in corporate. I use it all the time in research too. But I also use SPSS a lot, and I use a program called R, which is command line driven. And that's probably where you want to go to learn the new statistics is R and something called Python programming language. And so I like R, but to teach you R would be torturous for some of you because it's very user unfriendly because it's all command line driven. There's no clicking, there's no dragging. It's all basically typing in commands, and there's a different command for every different package you're using, and you got to have a list of commands to reference. It could be a mess. It's hard to remember all those things. SPSS is clicking and dragging, and it's much easier to remember how to do things. You have to kind of remember where the menus are. But when you're command line typing things in, it's kind of like using DOS. Before Windows, you had DOS. Some of you don't even know what DOS is, but it basically was a black screen that showed up and you typed into it to access your computer. There was no Windows or there was no MacBook. there was no Apple, right? It was just, a black screen and a little cursor showed up and you had to type into it. That's kind of what R is. But the R is also free. So if you're into data analysis, or hopefully some of you will be into data analysis, contact me and I'll talk to you about the different packages to use. But for this class alone, we'll be doing some stuff in Excel, which is pretty basic, but also useful at the same time. And the last thing on the list is a datum, which is a singular data point. So it's a score. We generally call it a raw score. So it's one person's score on one variable. Generally, if you have a datum, you're not going to do analysis on it because you only have one data point. You need to have data, and preferably a data set, which is all variables and all measures, to actually do analysis on. Now we talk about studying the sample and then generalizing it to the population. The population has values. So the population, which is everyone you're interested in studying, they're the target group, the target demographic, they have values. They have a mean. That group of 25,000 BMCC students has a mean. And that group of 25,000 BMCC students has a median, has a mode, has a variance, has standard deviation. So whatever value you're describing for the population is called a parameter. So the mean of the population would be a parameter. The standard deviation of a population would be a parameter. So any reference to a population, a measurement of the population, is a parameter. Any descriptive information pertaining to the sample is called a statistic. So if you find the mean of the sample of 100 BMCC students for their GPA, that's a statistic, because that's the measurement of those 100 people in the sample. If you were measuring the 25,000 BMC students in the population, that would be a population. The mean of that, that would be a parameter. The mean of that population would be a parameter. Many times your sample mean may not be the same as your population mean. Well, obviously, because you're only taking 100 people or so out of 25,000, or you're only taking 200 people out of 10 million, depending on what your population is. You're not guaranteed that your sample mean will be the same as your population mean. Most of the time, there are differences between the sample mean and the population. And that's why I tell you, you never prove anything in statistics. Because, can we be 100% certain under every condition that your sample mean is going to be the same as the population mean? You can't. Unless you take many, many samples over and over and over again, and then you find the mean of all those samples, combined samples. So if you find a mean of all those sample means, eventually it will equal the population mean. But most of the time, we're not taking an infinite number of samples. We're taking one sample to run our study. And so is that one sample mean representative of the population mean or not? Most of the time it's not. There's variation. Now, the bigger your sample, the better an estimate it probably is of the population mean, or the population standard deviation, or the population whatever. But if you have one sample and you're trying to say my sample represents the population, even if it does do a good job representing the population, to have exactly the same mean is very unlikely. And if you take another sample of 100 people, a different 100 people at BMCC, you're going to find they have a different mean than the first sample of 100 people. So now you have two samples with different means. And if you take a third sample, you're going to probably have three samples with different means, and so on and so forth. So there's always a little bit of variation between the sample statistics, including the means, and the population parameters, including the means, right? It's never the same, unless it's coincidental. So there are two branches of stats. One is descriptive stats, where we're summarizing and organizing the data. And we show lots of graphs. You can have bar graphs, you can have histograms, you can have box plots, you can have tables. That just describes the sample. So descriptive statistics describe the sample for the most part. Could you have descriptive statistics of a population? Yes. But once again, it's very unlikely, because how are you going to have access to the entire population? You're generally not. So most of the time, if you're using descriptive statistics, you're describing the sample. So you might say my sample of 100 students had 67 females and 33 males. The average age of my sample of 100 students was 22.6 years of age. You're just describing the sample. You're not talking about the population. You're just giving me a description of the sample. That's descriptive statistics. Inferential statistics is when I take my sample and I try to draw conclusions about the population. That's inferential statistics. And inferential statistics, there's errors associated with it, obviously, because your sample is not perfect. It's not necessarily the same as the population. So you're going to have, error involved. And so you may see the term margin of error, which you see in polling a lot, or you may see the term statistically significant, which means that based on our sample, we can draw a conclusion about the population with a high probability. It doesn't mean that it's proven. It just means there's a high probability that whatever hypothesis we're testing is supported by the data in the sample. And so as I was saying, that you don't have a perfect sample to population correspondence, you could have sampling error. So this is the discrepancy between the sample data and the population data. So more specifically, the discrepancy between the sample statistic and the population parameter. So the mean of your sample is not going to be the same as the mean of the population, which is the population parameter. That difference is called sampling error. This happens in polling a lot. These pollsters were really wrong in the 2016 election, where they all predicted Hillary Clinton would win all these states, and then she lost all these states by very small margins. And the reason why they were making errors is because when you're polling people, there's always a margin of error, because the polling is a sample. I polled 1,000 registered voters, and I asked them, who are they going to pick for president? Does that mean I know everything about every single person that votes? No. I called 1,000 people on the phone who are registered voters. How many people vote in this country? Probably half the country, right? So close to 200 million, 180, 190 million people probably vote. And I have a sample of 1,000. So I'm trying to draw conclusions about 180 or 190 million people that vote based on my sample of 1,000 people that I've polled. And obviously I can't be really, really confident. There's always going to be some sampling error involved. And so that's why you see plus or minus 4 points. So they're saying that based on our sample, we think that the true population mean, the people that vote for this particular candidate, is going to be within 8 points, 4 on one side and 4 on the other side. Now, that's a pretty big margin of error. That's a pretty big error rate, right? That you have 1,000 people, you're only confident, within these 8 points. And the reason is they can't interview every single person that votes. And then you also have the case of that, people vote. They may not tell the truth. They might tell you, yeah, I'm voting for candidate B, and then they go to the polls and they vote for candidate A. So now you have bad data. So there's a lot of problems with polling. And, in politics, the polling is a mess. And, the pollsters, their reputations have been really tarnished. And even the modeling people don't know anything either. I mean, they have models to predict. And, you have some pretty well-known modelers out there now that, try to predict elections. But all they're doing is running simulation based on a sample. So they're using sample data that they gather to then run a simulation based on the population. And they make certain, decisions in the model. And if their decisions are wrong, the model is wrong. And those decisions are human choices, like, well, they may have a decision that a certain number of people of this age group will vote for candidate A given a certain circumstance in the country. And if that premise is, that hypothesis they have is wrong, then their model is going to be wrong. And so you saw the modelers strike out in 2016 as well. So will it be better moving forward? I don't know. I'd be very hesitant about polling because there's a lot of room for error in any kind of polling. Here's a picture demonstrating sampling error. So in the population is 1,000 college students. The mean of the population in terms of age is 21.3. Now, if they take a sample of 5 people, now that's a really small sample. You wouldn't want to do that. But if they only have 5 people in the sample, look at their age of these 5 people. It's 19.8. So the mean age of the sample, the statistic, which is the mean age in the sample, is different than the parameter, which is the mean age in the population of 21.3. So it's 19.8 versus 21.3. And the same with sample 2. It's a little closer, but it's 20.4. Once again, you want to have a bigger sample. I mean, when you have a small sample, you're going to have a ton of sampling error. The bigger the sample, the less likely you're going to have sampling error, or it's going to be diminished. But pretty much even with a huge sample, you may not have the exact same value as the population. So this is how they would do research. You would gather, based on the population of college students, which is a huge population, you'd gather a couple of samples. And you have sample A, they have to read from a printed page. Sample B has to read from a computer screen. And then we test them on some variable. I don't know what they're testing them on. And then we look at their scores and we see the average of the sample of A is 26 and the average of sample B is 22. So there's a difference. But is that difference just due to chance? That means, is it due to sampling error? Just the fact that these are 2 samples from this bigger population, and they're probably not going to be alike. Or are these samples different enough to say that they come from different populations? That's basically the question we're asking. Are these 2 samples from the population, from one population? Or are these 2 samples derived from different populations given that there's different alternatives, given that reading from a computer screen is different from reading from printed pages? There would be 2 populations in that case. Or if they really come from the same population, that means there's no difference between these groups. They would come from one population. And then the difference would be due to just sampling error, chance, basically. So the question always comes down to chance. Are these groups different from chance, or are they different because whatever I'm manipulating, the independent variable, is different? And so that's why we need to use inferential statistics. Inferential statistics tell us, are these differences between these samples due to chance, or are they due to a real effect of the independent variable? And then we have to calculate our inferential stats and draw our conclusions. And that's basically what the majority of statistics is about, is take your sample, test it, and then draw conclusions about the population using inferential statistics. Inferential just means we go from the sample and generalize the results to the population. Scores are measures of variables that we're studying, and the process of measurement consists of defining how are we going to assess each variable that we're interested in studying. For example, let's say this is the problem in psychology. Let's say that you're measuring IQ. How do you measure that? You give everybody an IQ test. Okay, that would be a measurement, but is that a good measure? Someone else may say IQ tests are not really worth, not really telling you much about intelligence. They'd rather give people a test of EQ, emotional intelligence. Or do you give people a paper and pencil test? Do you give them a test on the computer? Do you give them a test where they have to solve puzzles? What do you really do to assess intelligence? It's such a hard concept to measure that different people will have different ideas. And that's the problem with measurement. But we do have a particular measure for each variable we're interested in studying. And we have to define that measurement. Just like I define intelligence. Intelligence is my variable, and my measurement is basically how I'm proceeding to assess intelligence. So intelligence in the previous example would be defined as a construct. We cannot directly observe it, but we can measure it indirectly. So if I look at you, I don't know what your intelligence is. Now, if you open your mouth and have a conversation with me, I have a better idea. And I'm drawing that inference through our conversation. Our conversation would be sort of an indirect assessment or measure of intelligence. Just like your IQ test score would be an indirect assessment or measure of intelligence. But I can't measure intelligence directly. Same thing as I can't measure depression or anxiety directly. I have to measure it indirectly. I could ask you questions about anxiety. I could measure your heart rate and your blood pressure, your skin conductance, and I can indirectly determine your level of anxiety that way. Is it perfect? No. Can you make mistakes? Yes. Is it frustrating as a researcher? Of course. Psychology is not physics. We can't just put people on a scale. We can't just we can't know the thermal point of the melting point of various substances. I can't directly measure the entropy occurring in the environment. I can measure all of that stuff in physics. So if you want to be 100% certain of what you're measuring, where there's no debate whatsoever about what you're studying, then physics and chemistry are definitely the subjects for you. If you're doing psychological research, it's not going to happen. Because there's nothing in psychology that we have an objective measure of. If I want to study stress levels, I ask you about your stress levels, or I give you some indirect test about it. But there's no way I can directly look at you and say, here, give me a blood sample, and I'll tell you exactly what your anxiety level is. Or give me a urine sample, or spit in this tube. I can measure cortisol through spitting in a tube, a stress hormone, but that's indirectly linked to stress. That's not a perfect measure. And that's just stress. I mean, everything else you're studying in psychology, I tend to study a lot of clinical health-related topics. I can't study any of that stuff. Anxiety, someone could look anxious, someone could talk anxiously, behave anxiously, but that doesn't mean they're 100% sure that they have this anxiety level. And someone else might come along and say, I disagree with you. I have a better way to measure anxiety. And then who's right? So that's what I mean. We have these constructs, which are characteristics we cannot observe, but we can measure. And they're at the heart of psychology, because psychology is the study of mental processes and their effect on behavior, and the study of behavior in general. But I can't directly observe. Even if I observe your behavior, I'm still making an inference. I'm still making a judgment. There's nothing like blood that tells me, you have, or here's my test for this particular pathogen, here you have this particular disease based on the lab results. There's no lab results. There's no clinical correlate that you can look at and say this person has this level of anxiety. You just don't know. So you have to kind of measure it indirectly. And the best way to measure constructs, which are measured indirectly, cannot be directly observed, is through operational definitions. So you define how you're going to measure depression. That's your operational definition of depression. Depression is the amount of times you refuse to go out with your friends in a week. That would be my operational definition of depression. So the number of times you reject hanging out with your friends and family in a week. Maybe I'm wrong. Maybe you have a better definition. Maybe it's the number of times you cry a week. That would be an operational definition. Or maybe it's number of calories you consume a week. That could be an operational definition of depression because people with depression change their eating patterns. Or number of hours you sleep per week because people with depression change their sleep patterns. And those would be operational definitions. They tell you exactly what you're measuring to measure the construct, in this case, depression. That does not mean you're right. So I may choose number of crying spells in a week as my operational definition of depression. And some other researcher would tell me, no, that's not a good definition. I have a better definition of depression. And then you get into a debate over who has the better definition of depression. Could I have measured depression a better way? What scale am I going to use? There's a whole bunch of scales for depression. Which one is better? And there's ways of telling that statistically, through reliability and validity. But a lot of these things, you're going with this is my best idea how to measure it, and I'm going to go with that. And if someone disagrees with me, that's fine. Maybe they advance psychology as a field by disagreeing with me, coming up with a better way. So there's no right or wrong, but there is room for debate. And that is the interesting part of psychology, but also the very frustrating part of psychology. Now that I've measured my variables, or I've come up with operational definitions of variables, I can talk about the different types of variables. You have discrete and you have continuous. Discrete means there's no intermediate categories. So like gender would be discrete. Because we have male, female, non-binary, we consider those separate categories. It could be a number of brothers and sisters you have in your family. That could be discrete also. So you could have 1 sibling, 2 siblings, 3, 4, 5, 10 siblings. But you can't have 3.765 siblings. Well, you might, but if you have 3.76 siblings, I don't really want to know about it because something bad happened. So you can't have these intermediate values. You can own 1 car, 2 cars, 3 cars, but you generally can't own 4.158 cars. Those are discrete variables. There's no intermediate values. Continuous variables are like GPA I talked about before. You can have an infinite number of possible values. So you might have 3.17 GPA and your friend might have 3.1653 as their GPA. See how there's so many different values. Between 3 and 4 in the GPA scale, you have thousands, if not more, tens of thousands of possible values. So a near infinite set of values between, major points on the scale. Those are continuous variables. So GPA would be 1. Your average on a test would be a continuous variable. You can have all kinds of fractional components there. Your weight and your height could be continuous as well because you have many different values. And you can measure height within, centimeters or decimeters, I guess, if you want, tenth of a center is 100, so I guess millimeters. Be kind of difficult to do that, but you catch my point. You can drag out height to many decimal places. Same thing with weight. You could break weight down into smaller and smaller units if you want, and you could have many different values for height and weight if you choose. You know, generally we have more than one value. We don't say this person's 6 feet tall, this other person's 5 feet tall, this other person's 4 feet tall. We generally break it into feet and then inches, and then sometimes it gets broken down into like even fractions of an inch. The same with weight. You can have pounds. You can break it down into, tenths of a pound, hundredths of a pound, if you so choose. So with continuous measures, we have something called real limits. And real limits are just these kind of imaginary boundaries where we would either round up or round down and they would fit into one category. For example, if someone scored 149.6 and someone else scored 150.3, those are two different scores, but we can comfortably lump them together into the 150 bin. So as you see, we round up 149.6 to 150, and we round down 150.3 to 150. So when we have a continuous measurement scale, we can then choose to set these real limits where we're either going to round up or round down to a measure on the scale. Now, the real limit here is, the individual unit is 1, but I could make the individual unit less than 1 if I chose. I could break it up into 0.5s and then do a real limit on those if I so choose. So the real limits are shaped by what your individual unit of measurement is, and they're only seen in the continuous variable. So real limits are boundaries of the interval responses representing scores measured on a continuous scale. Each score has an upper real limit, which is the top of the interval, usually round down from the upper real limit, and the lower real limit is the bottom of the interval, usually round up. Measurement assigns values to different events and categories. So whenever you have a variable and you measure that variable, you're going to have a measurement. And that measurement can be discrete, it can be continuous. That means the value can be in terms of categories. So you have what is called categorical variables. More technically, they're called nominal level variables. They are basically, you belong to this group. And then you have continuous variables, which can be generally interval or ratio scaled, which we're going to get into shortly. And they fall into the continuous level of measurement, and there's many points on the scale. So these are our four main levels of measurement. Nominal is the simplest at the bottom of the scale. It's the simplest. It's just a label. So gender is a nominal variable. Diagnosis, whether you got the experimental condition or the control condition. I said before, ethnicity, socioeconomic status, you're rich, poor, or middle class. Right? So anything that's a category is a nominal scale. That's the simplest of all measures. Anything that has a rank order is an ordinal scale. So your clothing size, you're either a small or extra small, small, medium, large, extra large, double XL, etc. So we know based on those values, small, medium, large, that large is bigger than medium, which is bigger than small. So clothing size is ordinal. Olympic medals, you want a gold medal is better than the silver medal, is better than the bronze medal. So they're categories, but they're also rank ordered. You finished first in the race, you finished second in the race, you finished third in the race, you finished 50th in the race. Those are categories, but they're arranged in order, so it's an ordinal variable, ordinal level of measurement. Interval is an ordered category. So these are continuous variables that have equal distance between points on the scale, and they have an arbitrary 0 point. A lot of psychological variables tend to be interval scaled, especially if you're measuring it with a scale like a depression scale. You scored 80 on the depression scale. Your friend scored 70 on the depression scale. Therefore, you scored 10 points higher on the scale than your friend, because there's equal distance between points on the scale. So if you're 10 points higher, if I was breaking it down into ordinal, you would be first in depression and your friend would be second. But if I say you're first in depression and your friend's second in depression, doesn't really tell you what your depression is. It doesn't tell you how far apart you are, right? You could have a tremendous amount of depression and your friend could be fine. So you could be up near 100 and your friend could be near 0, and you would get 1 and they would get 2 if you were doing ordinal scale. So it doesn't really tell you where you are relative to everybody else. It just tells you what order you're in, but not how close together you are, right? With an ordinal scale, you can have someone win the race, like Usain Bolt could win the race. Like, let's say Usain Bolt is racing against you. Now, maybe you are, a good runner. I don't know. I used to be a good runner years ago, but my back does not permit me being a good runner these days. But no, Usain Bolt's, come on. If you were racing Usain Bolt, you would finish 1. I mean, actually, no, he would finish 1, obviously. You'd finish 2, right? So you could say, I finished right behind Usain Bolt. But Usain Bolt ran the marathon in an hour and 50 minutes, or whatever race he's running these days. He doesn't run marathons, but he ran the race in whatever crazy time he ran it in. And you ran the race, but it took you 5 times as long to finish. From an ordinal perspective, he is 1 and you are 2. And so you feel good about yourself, like, I finished right behind Usain Bolt. But from an interval perspective, he finished in 2 minutes and you finished in 20 minutes. So if it was on an interval scale, you're no longer 1 and 2. You are on an ordinal scale 1 and 2. But from an interval scale, he's at 2 minutes and you're at 20. And so people can really see the distance between the two people that ran the race. And so the interval scale provides you more detail because it tells you not only what order the data is in, but it also tells you how spread apart the data are. Now, there's no true 0 point either for an interval scale. So interval scale is anything where if you get a 0, the 0 does not mean that you absolutely lack the quality, that construct completely. For example, if you took a stats test and you scored a 0, I'm not saying you're going to score a 0, but hypothetically you scored a 0, that doesn't mean that you have no knowledge of stats. Well, you might say, well, I scored a 0, so I obviously didn't know anything. That's not correct. Maybe you did know something, but I just didn't ask it on the test. So the 0 on the exam in the stats test does not indicate that you have no statistical knowledge whatsoever. It indicates that you don't know what you're doing in the class. You didn't try, probably. But maybe you did know something, I just didn't ask it. So that 0 doesn't mean a complete absence of the construct. So that 0 on the test doesn't mean you know nothing about stats. It just means you performed very, very poorly. You probably didn't know much at all, but it doesn't mean that you knew absolutely nothing. Okay? So you think of a temperature as an interval scale. When it's 0 degrees Celsius, does that mean there's an absence of temperature? And the answer is no. There is temperature. It's just damn cold if it's 0 degrees Celsius. It's freezing. But it doesn't mean there's an absence of temperature. There is temperature. Temperature is heat. So there is still some kind of heat at 0 degrees Celsius. So that 0 on the Celsius scale is not a true 0 point. Therefore, the Celsius scale is interval. Same with Fahrenheit. If it's 0 degrees Fahrenheit, is it cold? Yes. Does it mean that there is no temperature? Of course not. just cold. Doesn't mean lack of heat or lack of temperature. So Celsius and Fahrenheit, those 0 points on the scale do not represent true 0 points. Now we move to ratio. Ratio has the same properties as interval, which means equal distance between points on the scale, but there is a true 0 point. And you can make ratio level comparisons using a ratio scale. For instance, if it's 80 degrees Fahrenheit, is it twice as hot as 40 degrees Fahrenheit? And the answer is no. You might say, oh yeah, 80 degrees is twice as hot as 40 degrees Fahrenheit, but that's not the case. You can only make those kind of ratio comparisons if you have a true 0 point. And since Fahrenheit does not have a true 0 point, you cannot say that 80 degrees Fahrenheit is twice as hot as 40 degrees Fahrenheit. You could say it's 40 degrees hotter. 80 degrees is 40 degrees hotter than 40 degrees Fahrenheit. You could say that. But you can't say that it's twice as hot. However, if you have a ratio scale, you have a true 0 point. So for an example of that would be temperature in terms of Kelvin. So if it's 0 degrees Kelvin, guess what? We're all screwed. We're really in trouble when it's 0 degrees Kelvin. Has it ever been 0 degrees Kelvin? Thankfully, no. Not on this planet. In a lab somewhere, they got close to it, but I don't think they have actually attained 0 degrees Kelvin. Even in the lab, I think they've become fractionally, percentage of a decimal point close to 0 Kelvin, but never at 0. And the reason is, if it's 0 degrees Kelvin, there is no temperature, there is no heat, and the molecules stop moving. Everything freezes. It's called absolute zero. So if you look at Kelvin, 0 degrees on Kelvin actually means there is no temperature. So therefore, 0 degrees Kelvin has a true 0 point, and anything with a true 0 point is a ratio scale. So all physical measurements tend to be ratio scaled. Height, weight, time, these are all ratio scale measures. So if it took you an hour to run the race, and your friend took 30 minutes to run the race, your friend is twice as fast as you are. Because time has a true 0 point. So if something takes 0 seconds, it doesn't actually exist, right? It's a complete lack of an event. If something is 0 degrees Kelvin, it's a complete lack of temperature. If you weighed 0 pounds, you'd have a complete absence of weight. So on and so forth. So you see, like, these physical measurements, they tend to be ratio scale. In psychology, most of our measures are going to be interval scaled. All these scales that we use to measure different variables, they're interval scaled. All the assessments you take in school, the tests, the quizzes, they're interval scaled. So next time you get that 0 on an exam, and you say, I knew nothing about the test, I know nothing about the subject, you're wrong. You didn't score absolute 0. You got a 0 means you really didn't know much. You probably know very little about the topic. But there might be something that you do know, it just wasn't asked. It wasn't assessed. So 0 does not mean on an exam or on a scale, does not mean complete absence of that quality. It just means you did it really bad. So moving on, we talk about descriptive research, where we're studying basically the structure of the data, and we're not trying to make inferences from the sample to the population. If we're looking at variables based on individuals, we have one or more variables that are measured per individual. And so these things can be easily coded in research. You could code someone's gender, right? You could code someone's ethnicity. You just give them an arbitrary number. For example, I might code male 0, female 1, non-binary 2. I'm giving them an arbitrary number as a code for the variable, for the category they belong to. and that would be a nominal variable. And I'm using that purely in descriptive fashion, but I can also use that in an inferential test, like if I'm doing some kind of ANOVA or t-test, which I will be doing later in the semester. We can also look at the relationship between variables that are measured. Now, the best way to look at relationships are looking at two continuous variables, two or more continuous variables. If we're looking at two or more continuous variables, we can do correlation to see if they're related. If we're looking at two or more nominal variables, we can then do something called chi-square, which I hope to get to at the end of the semester, which looks at the relationship between nominal variables. And this is kind of, I jumped ahead a little bit. When I'm looking at correlation, I have at least two variables for each participant. So I have to have two measures for each participant at minimal to do a correlation. So the most common one you've probably heard a million times is height and weight. So what's the correlation between height and weight? Well, you have two variables. You have a variable height, you have a variable weight, and we know that those two values are positively correlated, those two variables, height and weight. So as one increases, the other increases, or as one decreases, the other decreases. You must have at least two variables to do the correlation, and you must have multiple participants. You can't have one. You got to have at least a handful, preferably a lot more than that. And then you, based on that correlation, you could tell me if it's a strong correlation, a weak correlation, or no correlation. You can also tell me positive or negative. And these are used in non-experimental designs, which are basically mostly surveys. So if you're doing surveys, you're always doing correlation. Here's an example of correlation. You see you have 1, 2, 3, 4, 5, 6, 7, 8 students. And we're looking at Facebook usage and academic performance. And this is always one of my favorite examples to look at, although now you're saying Facebook is for old people. Well, probably now, but it's been studied a lot, Facebook. Same thing with Instagram or Snapchat, or, number of times you're doing the, what is this other one that everyone does now? The one you make the videos. TikTok. Used to be called Musical.ly. Now it's called TikTok. Number of TikTok videos you make in your academic performance. And you'll see that there's usually this pattern that you see on the screen of the scatter plot here, which is the makeup of the correlation, pattern of observations between Facebook time and academic performance. So the more time you spend on Facebook or other social media outlets, in general, the less you perform academically. And that makes a lot of sense, right? You're on Facebook, you're on Instagram, you're on Snapchat, you're on whatever, you're not studying. You got your phone by you when it rings, and you hear the alert, you get the notification, you're looking at your phone, then you look at your book, and 10 seconds later you're looking at your phone, and guess what? You learn nothing. So things were a lot easier when I was a kid, and we didn't have smartphones. How did we live? We actually had things called payphones. You might actually see a payphone in the museum now. If you've never seen a payphone, you can actually Google it. There were things called payphones. And they were phones in a booth, and you had to actually put change in them. And you used to call your parents collect because you didn't have change, so you just said collect call, and they would charge your parents like $10 a minute. And you were like, okay. Payphones, Google it. If you don't know what payphone is, there were no smartphones, you had payphones. So the benefit of having payphones is you weren't looking at the payphone every 2 seconds while you're studying. You didn't have your smartphone, you didn't have social media. So I actually believe it's a lot harder to be a good student today, modern times, if you want to call this modern times, than it was many years ago. It's so much harder because you're being bombarded with social opportunities. It's how do you focus? It takes a lot more discipline. And so this graph shows you, this is real data. I mean, there's so many studies replicating this. The best thing to do is put the phone away, especially when you're listening to my lecture. Now, could you watch my lectures on YouTube on your phone? Yes, that would be a good use of your phone. If you watch my videos that I record on your phone while you're traveling or you're at work or you're on the couch or whatever, put your phone on, watch my videos, but stay off of Facebook, Instagram, Snapchat, all that stuff because you'll learn more. Just watch me. I'm more entertaining than all these other social media sites. Don't worry. I told you about payphones. Now you can tell your friends. Tell your friends there was a rumor there were things called payphones that existed. There were no smartphones. Can you imagine that? Can you imagine a world like this? Boy, it was so primitive. And there were also Neanderthals living among us. Oh, sorry, I'm off by about 63,900 years. Okay, moving on. Limitations of correlations. Correlations cannot show cause and effect. Obviously, you probably know that from Psych 100. They do not provide an explanation for the relationship. That's up to you. If you find variables to be positively or negatively correlated, you need to explain that. Sometimes you can easily, and sometimes you can't. Sometimes you get correlations and they make no sense. And you need to try to figure them out. Or sometimes they're due to outliers. Like you have some screwy data point that doesn't really belong there. Someone answered something, they weren't paying attention, or they provided a bad answer, or they couldn't understand the question, and they give the answer and it screws up your data. And it gives you a correlation that's maybe not indicative of what's happening in the population. So correlations are a guide, but they are not the end all, be all. And they definitely do not indicate causality. There's no causation in a correlational method. You could also compare two groups of scores. So instead of looking at the relationship between two or more variables, I could look at differences between two or more groups. And if I look at differences between two or more groups, I'm usually looking at the means, the mean of group A and the mean of group B, and I'm usually manipulating an independent variable. So group A gets the study sessions and group B gets nothing. And I want to see if study sessions affects your test performance. So I compare group A and group B, and I hope that group A that gets the study sessions do better than group B. So I'm comparing those means. That is done through inferential stats like a t-test. If I have two groups, it'll be a t-test. If I have three groups, it'll be ANOVA. If I have multiple variables with two or more groups, it'll be factorial ANOVA. And it goes on and on and on. It gets more and more complex because then I can have actually I can have more than one independent variable. I can have more than one dependent variable. And then I get into multivariate analysis. So the basic situation is two groups, compare them, see if one group is better than the other, and draw the conclusion, draw the inference using the inferential stats that we're going to learn in this class towards the second half of this class, or towards the sort of the beginning, middle of the class we're going to start it. Here's an example. I have one independent variable here, video games. I give half the participants a non-violent video game, and they play that non-violent video game. I give the other half a violent video game, and then I compare them. I compare them based off aggressive behavior. So the aggressive behavior is my dependent variable. And I want to see is the mean of the violent higher than the mean of the non-violent in terms of aggression. And if that's the case, and it's not due to chance, because we always have to compare against chance. If it's not due to chance, then I say that violent video games lead to more aggression compared to non-violent video games. And I would also want to use random assignment here and things like that to make sure that there's no what are called confounding variables or extraneous variables. So the goal of the experimental method is to demonstrate cause and effect. So I generally take one variable and I manipulate it. Just like you saw in the previous example, you either get the violent video game or you get the control, which is the non-violent video game. And so the control gives me a comparison group where I can say the video game is causing the aggression because now I'm comparing it to the control, and everybody gets treated the same except for the video game. So everybody's the same, gets treated the same way except for one group gets a violent video game, the other group gets a non-violent game, and then I could say does violent influence aggression. So the independent variable is the variable manipulated by the researcher, and the dependent variable is whatever you're measuring. It's the outcome of the study. In the previous example, the independent variable is video game violence, and there are two levels of the independent variable. There's the violent video game, and then the second level is the non-violent video game. The non-violent video game is also known as the control group. And the dependent variable in the previous example is aggression. How do I measure that? It could be a scale. Could be I'm measuring aggression by watching people in school, how many outbursts they have, how many negative verbal interactions they have with people, any physical interactions with people, like fighting. So there's a variety of ways I can measure it. You need to find the operational definition of aggression. And we think that the independent variable will affect the dependent variable. So in this case, video games, whether you get violent or non-violent video games, will affect aggression levels. And if that's the case, then I can say that aggressive video games causes an increase in aggressive behavior. Now, how do I draw this cause and effect conclusion in an experiment? I need to have random assignment, which means that I have to flip a coin, and if you get heads, you go get the violent video game, and if you get tails, you get the non-violent video game. So I need to make sure that everybody's assigned to the two groups by chance. And the easiest way with two groups is flipping a coin. I could do matching where I put a certain number of men in one group, a certain number of men in another group, a certain number of people of a certain age range in one group, and then match them in the second group. I could do that. That's not as effective. Personally, I don't like matching because matching doesn't completely eliminate any kind of alternative explanation, which is known as a confound. The matching is okay if you have no other choice, but if I could randomly assign people to conditions, that's much better than matching. The control condition does not receive the experimental treatment. They either receive a placebo or a neutral treatment, and they're used as a baseline. The experimental condition are the people that actually get the treatment. So the group that got the violent video game would be the experimental group or condition. The group that got the non-violent video game would be the control group or the control condition. You could have a non-equivalent control group where you don't control who's in each group, like they're pre-made groups. For example, you're studying people that are the victims of trauma, and you're comparing them to people that have no trauma. Well, I can't randomly assign people to trauma. I can't say, hey, you're in the trauma group. I'm going to make your life miserable. I'm going to do something horrible to you so you're traumatized so you can be in the trauma group. That would be kind of unethical. So we can't just assign people to groups like trauma. So we have to use people that already have a real life trauma. So if I'm studying trauma, I can't randomly assign. I got to use what are called non-equivalent groups, or what we call, mainly we call this a quasi-experimental design. And we call this variable a quasi-independent variable, which means quasi means somewhat. So this is kind of a somewhat of an independent variable. They're preformed groups. So you do this with, if you're studying people that are trauma, they're already preformed. If you're studying people with drug addiction, you can't say, hey, you're randomly assigned to the drug addict group. You are now going to become a drug addict. Can't do that. So you go out and you find people that already have drug addiction, because you can't just assign people to become drug addicts. So if you're studying groups of people that you cannot easily randomly assign to conditions, you have to do these non-experimental methods. These are mostly called quasi-experimental designs. You also can have a pre-test, post-test design, which is when you measure someone at two points in time. So this is also known as repeated measures, by the way. I do this a lot in my own research. I have a pre-test, and then I have an intervention, and then I have a post-test. So my intervention is generally meditation. So I do like 8 or 10 weeks of meditation with people. I measure them before, I do 10 weeks of meditation, and then I do a post-test afterwards. And I look to see, does 10 weeks of meditation, how much of an effect does this have on their academic performance, but also their well-being, their depression, their anxiety, their stress levels. their interactions with family members, friends, etc. And what we find is we find huge differences when we give 10 weeks of meditation to BMCC students. It makes them so much better overall. They feel better, and they're just thankful they had the opportunity to do this sort of thing. But that would be an example of a pre-test, post-test design. I take a pre-test, I do the intervention, and then later on I take the post-test and I see if there's a difference. So here's gender. Gender is a quasi-independent variable. So this is a quasi-experimental design here, where I look at the difference between boys and girls. Obviously, I cannot randomly assign people to be either in the boy group or the girl group. Those are already preformed groups. The dependent variable is verbal test scores, and if I want to see if there's a difference between boys and girls, I measure them, and I find the two means, and I compare the means. And I see, is this a difference due to chance, or is this difference due to the fact that gender is playing a role? But this would be an example of a quasi-experimental design, because you have boys and girls, and those are preformed groups. You cannot randomly assign here. Here's another example of a pre-test, post-test, right? You have before therapy and after therapy, and you're looking at depression. So here you're not randomly assigning either. You're doing pre-test, post-test, or what is called repeated measures design. And you want to look for any differences between therapy before and therapy afterwards. And we hope that after therapy, depression scores go down. That's what we would hope happens. We have to see, is that a real difference, or is it due to chance? Now, I don't expect you to understand when I say, is it a real difference, or is it due to chance? Because it's a little more complex that we'll go into later in the course. But remember, we talked about sampling error. A lot of times, the data can be different from the population parameters, right? The sample statistics can be different from the population parameters by chance, just because it's a different sample. And that's the same thing going here, right? It could be that their scores after therapy are the same as they are before therapy, but the numbers are different just due to sampling error. I took two different samples, I'm going to have two different means, right? That they both come from the same population of people that have, that are not going to therapy, right? And they just happen to be different by chance, versus they're different because it's not sampling error. It's not just due to chance. I took two samples, I have two different means. It's due to the fact that the therapy is working. So that's the issue here. The chance is therapy, therapy has no effect, and I took two different samples, I got two different means. That would be chance. That's also known as sampling error, that the sample means are different than the population mean. If it's a real effect of the independent variable, if it's a real effect of therapy, the groups are different, not due to chance. Yes, there probably is some chance involved, but the difference is so big that it's not due to just chance. It has to be more than chance. And if it has to be more than chance, it has to be because the therapy is working. And the overall, rule of thumb is the bigger the difference between the groups, the more likely it's due to the independent variable and not due to chance. The smaller difference between groups, the more likely the difference is due to chance and not due to the independent variable or the treatment you're using. So if that difference is big enough, it's probably not chance, it's probably the therapy is working in this situation. So as I said before, go back and review Appendix A. We refer to scores as X and Y. So X is the first variable we're looking at. Y would be the second variable. If there's a third variable, you can call it Z, you can call it W. These are just variable notation. It doesn't really matter, it's arbitrary, but we generally refer to it as X and Y. So when I do a correlation, it's usually X and Y. When I do the mean of a variable, I usually use X to represent the score. X represents the raw score. N is generally the number of scores in a population, capital N, and lowercase n is the number of scores in a sample. So those are just some basic statistical notation. You're going to see this throughout the course. And you may see the summation sign comes up. This means sum or add everything up. So whatever's following this sigma, this Greek letter, capital sigma, whatever is following that, you're going to add everything up. So if it says sum of x, that means you add up all the scores, all the raw scores. So a lot of times you'll just see sum of x. That means add up all the scores that you see, right? If you see sum of y, that means add up all the y scores. So there's two variables, x and y. It says basically add up the y, the second variable scores. So sum of x would be the first variable score, sum of y would be the second variable scores. That's what we see mainly. And you might see square, and you might see, you know, in parentheses, and we're going to be talking about that, and that'll start in chapter 2. But just look at the summation rules, and you have to always follow the order of operations. So PEMDAS, parentheses, exponents, multiplication, division from left to right, addition, subtraction from left to right. And if you do that, you'll be fine. So review Appendix A, read through the rest of chapter 1. I hope this walks you through it and gives you an idea of what's going on. And if you have any questions, you can always contact me. And then next week, we'll be working on chapter 2 for the next time. And keep up to date, do the readings. Do the readings first, come watch the lectures. And if you have any questions, you can always office hours or email. Hope you enjoyed. See you soon. Bye for now.